do that wrong, but there's any.
You actually did something very good there, which is that you put in some numbers. What number did you call this?
1,
And what number did you call this?
5.
Good. So that was excellent that you put in those numbers. So then you might as well carry that through and put the numbers in your product. That way you know whether you're getting it right. 4, 3, 2, 1. Now we know that number 1 is forming a bond to number 5. And then 6, 7, 8. So of course these are not IUPAC numbers, they're just reference numbers. So it actually is a really good habit to put in the numbers when you're drawing this product, but we should put the numbers in the product as well. What do we call these steps? These are our termination steps. Why do they terminate the chain reaction?
Because they get rid of a radical.
Yeah, if there's no radical left over, you must be terminated. Notice that every propagation step always gives you a radical, so it's not a termination step. I noticed that one of the termination products is the same as the product from propagation step 2. But they're still different steps because propagation step 2 allows the chain mechanism to continue while this terminates it. Which of these steps require energy?
The first one and propagation step 2 from the radical.
Well, which of them requires the heat or the light?
Oh, the initiation step.
Yeah, so it would have been better to actually put in the light or the heat.
I did.
Oh, I'm sorry, I missed that. All right, very good. Then good job putting in the light or the heat in front of initiation step 1. Now, I think you said that propagation step 2 also needs the light or needs energy.
Needs energy from the radical.
And we really shouldn't say that because propagation step 1 and propagation step 2 are equivalent. Both of them are getting rid of one radical and forming a new radical. Both of them are getting rid of a radical and forming a radical. Neither of them really needs much external energy because, again, they're kind of self-sustaining. The energy they get from getting rid of one of the radicals can be used to form the other radical. This is the one that needs the heat or the light. That was good. I think you can see you've already made a lot of progress here. I think there was a couple points where you kind of hesitated and didn't quite know what the next step was. And again, one thing that might have helped you is just to remind yourself that overall, you're going to be removing a hydrogen and replacing it with a chlorine. And we've got to remove the hydrogen first and then replace it with a chlorine. So propagation step 1 is when we remove the hydrogen. And propagation step 2 is when we replace it with the chlorine. If you remind yourself what you're trying to do, that makes it much easier to remember what happens in propagation step 1 and propagation step 2. The role of the initiation is to give you some radicals. Then propagation step 1 removes the hydrogen, which makes room for propagation step 2 to put in the halogen. And then we can figure out the termination steps by just combining all the different types of radicals that are produced at any point in reaction. Well, we had 2 different types of radicals here, ethyl radicals and chlorine radicals, and here's the 3 different types of combinations that you have. Oh, okay. Last time we saw how important it was that when you attach something to a substrate, you should always ask if you're forming a stereocenter. So did we check that here? Did we form a stereocenter when we attached this chlorine?
No, because there's 2 hydrogen.
That's right. So do we need wedges or dashes?
No.
No, so how many products do we get?
1.
Yeah, so this was correct. But we got to watch out for that. If we've been forming a stereocenter, we have to take that into account. So that can be an issue on radical halogenations. Stereochemistry can be an issue. I saw that the instructor was testing that in some of the questions. It wasn't an issue on the 2 ones we've done so far because we weren't forming stereocenters, but we have to watch out for that. Now, there's also a regiochemistry issue here. After you did the initiation step, you showed the chlorine taking this hydrogen. But it could have taken a hydrogen from here. So we got to go through this all over again. We have to consider what happens when there's more than one region that can react. Okay. Previously we saw regiochemistry for alkenes, and here's the regiochemistry here. The chlorine might have taken this hydrogen, or it might take this one. All right, so to make some room, I'm going to erase the termination steps. Now let's draw in a new propagation step 1. Let's draw what the propagation step 1 looks like when the chlorine takes one of the internal hydrogens, because that can definitely happen.
Propagation step 1?
Yeah. You showed what happens in propagation step 1 if the chlorine steals the terminal hydrogen, but it's easily possible it could steal the internal hydrogen, so we have to show what that would look like. Good. Now we have to draw this hydrogen. Excellent. Let's keep going to propagation step 2.
Let's do the same thing.
You're doing good. What's the name of this step?
Propagation step 2.
Yeah, so in this problem, there are different possible propagation steps, different possible paths that we can follow. What would be most likely to have happen after this propagation step 2?
Another propagation step 1.
Yeah, we could do another propagation step 1, and it could either be like this or like this. Either of these are possible. Good. Good. Now, did you remember to check whether you were forming a stereocenter?
We are this time.
Yeah, we are. So let's take that into account. Well, sorry.
2 products, maybe?
How do we know? What is the geometry of a radical? Tetrahedral, trigonoplanar, or linear?
It's a squiggly line so that you don't have to determine one or the other. You can just say it could be one or the other.
Let's see. Let's see. I'm not quite sure if I follow. It sounds like you're talking about some notational trick that your instructor might have talked about. But let's put that aside for a second. Let's just decide what is the geometry of a radical? Tetrahedral, trigonoplanar, or linear?
I don't know. I'm going to guess it's tetrahedral.
Do you know what the hybridization is of a radical? sp3, sp2, or sp?
Since I said it's tetrahedral, I guess it's sp3.
Those would go together. However, it turns out that radicals are sp2.
Okay.
That just has to be memorized. We're simply going to have to memorize that radicals are sp2 hybridized.
Are they still tetrahedral?
So they can't be tetrahedral.
So they're trigonoplanar.
They're trigonoplanar. That's right. All right, so we'll simply have to memorize that hybridization. Radicals are sp2. So what did we say their geometry was?
Trigonoplanar.
So when this chlorine attacks, will it attack from in front, from behind, or both?
Both.
So how many products do we get?
2.
All right, so we're going to have to draw both of those. Now, I think what you might have been thinking of is that maybe your instructor gave you a shortcut where you just draw a squiggle to show.
Yeah, to show both.
Okay. Most instructors for this question would want you to show both the wedge and the dash.
Okay.
Obviously, if your instructor has given you some shortcuts, you can follow those, but it's certainly safest to draw one picture on the wedge and one picture on the dash. Would we expect these to form in equal amounts or unequal amounts?
Those two in
Yeah.
equal amounts?
Yeah, because there's no distinction between the front and the back of this molecule, so we get a racemic mixture of these two enantiomers here. So that's something you have to watch out for on these problems, regiochemistry and stereochemistry. The regiochemistry is that there could be more than one hydrogen that can be replaced. So you have to make sure that you draw a product for every single hydrogen that can be replaced. And the stereochemistry is that if you are forming a stereocenter, you're going to form both the R and the S enantiomers. So you have to show both of those. Are there any other hydrogens we could have replaced? Or are we
No,
done?
because it's the same
Yeah, if we take off this hydrogen, it's really symmetrical to taking off this hydrogen, and this hydrogen is symmetrical to this one. So these really are the only products. So here we get this product, and this product. So I did see a problem like this in the handouts where he said draw all products, including stereoisomers, and this is exactly the kind of thing that you would be going for.